the slide, well, the so-called slides. And you can hear me, right?
Yes, perfectly. Okay, so for the last talk of today, it's a pleasure to listen to Bakhtin from Quant Institute. We talk about dynamic polymers. So please go ahead.
All right, thank you. So this talk is about dynamic polymers. It's joined with my students Kongbin Chen and Ling Li. Ling Li, so with him we did mostly the static polymer work, and with Hongbin, so he's really responsible for collaboration on dynamic polymers. So instead of giving you a plan of the talk, let me give you some keywords. So we are trying to, in this talk, we're trying to analyze directed polymers, which is, there's a collection of models based on Gibbs distributions for random paths in random potential, in random environment. And we are trying to analyze these Gibbs measures from the dynamical viewpoint, trying to interpret them as invariant measures for infinite dimensional stochastic gradient flows. And so there is a bunch of keywords. We are interested in those invariant measures and Gibbs measures, in the monotonicity emerging in those systems. There is a phenomenon that we call ordering by noise. And we also managed to prove one force one solution principle on each ergodic component of the emerging random dynamical system. So this is an SPD conference, and I need to show you one slide about stochastic PDEs, because the initial motivation for me was the ergodic theory of stochastic Burger's equation. So that's the first slide here. I mean, I could have given this talk without this slide, but this is my connection to stochastic PDEs. The Burger's equation is this, one of the basic nonlinear equations. I'm discussing this in 1D. There are multi-dimensional versions of this. Well, in the fluid dynamic interpretation, U stands for particle velocity. So at each point x, at each time, there's a particle on the real line, and the velocity of that particle is called U. And so this equation basically says that these particles move under external acceleration implied by the external forcing F, and there's friction, which results in this viscosity term. So here kappa over 2, so that's the viscosity parameter. So the Laplacian is due to viscosity. So in this work, the external forcing small f is going to be random. So it's generated by a random potential, capital F. And in principle, it can take various forms. There are various models. We are taking it to be this kind of kick forcing, and it means that it's applied at each integer time, and between those kicks, the system evolves without external forcing. So at each integer time there is a potential F, which is so from k to k. So these are IID kicks, and it's stationary and mixing in x. So x is continuous variable, and now time becomes the discrete variable. And there are just a couple of basic assumptions on f. So it's stationary mixing in x, and there's some regularity, and it should have there's some moment condition. It shouldn't be too large. And now the standard approach to those systems with quadratic nonlinearities is to apply the Hopf-Kohl transformation, reducing the system to the heat equation. In this case, is the heat equation that also has multiplicative kicks. yeah, you can solve that with the discrete version of Feynman-Katz formula. So it's just like the the Feynman-Katz formula that you all know, except instead of the Brownian motion for the usual heat equation. So this is time discrete, and so this is based on Gaussian on a Gaussian random walk, and it's modified. The exponential weight is modified by the external potential Fk. So the main point in this formula is that you can view this as an integration with respect to a polymer measure. So you have this Gaussian measure, and on top of that, there are these random inputs from the environment. And so you can view this as a Gibbs measure, defining a distribution on those paths with self-interaction. So the self-interaction is quadratic. So that gives the Gaussian term, and also there is this external interaction with the environment. And so this is one of many polymer models. So in this talk, I will be mostly talking about this one, but I'll give some references to other useful polymer models. What this formula really means is you take point x, at time n, and from that point you can emit the Gaussian random walk back in time, and you're integrating over all those Gaussian paths. You're integrating the exponential weight that corresponds to the external potential, and also the initial condition. And if you're interested in studying long-term properties of the Burger's equation, or KPZ stochastic heat equation, you're interested in studying those polymer measures over a long time. And ergodic theory of the Burger's equation that is based on these polymer measures. So that's my joint papers with Li and Li, and that extends the previous work for zero viscosity that corresponds to zero temperature polymers. And so that's joined with Eric Kator and Kostya Khanin, and there's also my own separate paper. So now from now on, I will be mostly talking about directed polymers, and I'll sort of forget about the Burger's equation. So what is a point-to-point polymer? So you fix 2 points at 2 times. So here the times are 0, and then and you consider paths connecting them. So these are integer times indexed paths. So these are going to be subject to self-interactions and interactions with the environment. So you define this energy that combines these two. And you have to take, if you want to introduce a Gibbs measure, you have to define the temperature or inverse temperature. So that's what you do. And in the end, you're considering the measure with all those indices here. And this measure is defined as it's absolutely continuous with respect to the bag. The density is given essentially by this exponential weight. And you have to normalize by partition function z to obtain a probability measure. So this is a random probability measure on paths. As always with Gibbs distributions, it's a very natural question to ask what happens with those in the infinite volume limit. So that's the so-called thermodynamic limit for Gibbs measures. So in this case, it's infinite length, but I'll keep saying infinite volume because that's the standard terminology. So the top part of this slide is just the same thing that you saw on the previous page. But there is, in principle, there is a difficulty in defining infinite volume Gibbs measures because the energy is infinite, right? If you consider the infinite volume path, then you'll have infinitely many terms there. So instead of dealing with infinite energies, you have sort of to localize, and that's standard in statistical mechanics and mathematical statistical mechanics. And you're introducing this DLR condition, Dobrushin-Lanford real condition. And so a measure on infinite paths is called infinite volume polymer Gibbs measure with this potential, with this energy. So you have to fix the endpoint. So it's an infinite volume polymer measure with this endpoint. If conditional distributions on finite paths, given the tail, given the exterior of a finite box, so if these are given by the exponential formula that I already have shown you. So this is a standard way to define infinite volume Gibbs measures. They are defined by by a system of conditional distributions on finite volume box on finite boxes. And then the standard question in statistical mechanics is it's one of the first questions you could ask and you should ask is existence and uniqueness of those infinite volume polymer measures, Gibbs measures in general. The natural way to state this is, do local interactions of this polymer chain with itself and with the environment. So does that define the macroscopic state uniquely? And if it doesn't, then what are possible macroscopic states? And with Lee, we prove this theorem. We prove this theorem where we show that for each asymptotic slope v, so if I fix this v that plays the role of asymptotic slope, for each asymptotic slope, there is a unique infinite volume polymer measure concentrated on paths with that slope. And the way to obtain those measures is really to take a limit. So you fix 2 points, you consider the Gibbs measure on polymers between them, and then you take point xn to infinity in that direction, and the associated measures on finite paths, they will converge weakly. So this is what this arrow stands for. So you will have a weak convergence. In this case, this is just finite dimensional distributions, really. You have to you'll obtain a convergence statement to a measure on infinite paths, and that measure is a unique infinite volume polymer measure concentrated on paths with that slope. So for each slope v, you have a unique infinite volume polymer measures. And well, then the obvious plan was to use these measures to prove unique ergodicity, uniqueness of invariant distribution on each ergodic component for the Burgers equation. And that's what we managed to do. In principle, this question can be asked for every polymer model. What happened? Describe the infinite volume polymer measures. And so there's a bunch of other polymer models that people have been studying, and in principle, you can ask what happens with other energies here. What if the self interaction is not quadratic? What if the dimension is higher than 1? What if the potentials are not IID? What if something else happens? What happens for lattice models? And all of that is open, except for a couple of cases where you have exact solvability. So the situation that is known to that I know the answer, where existence and uniqueness of infinite volume polymer measures was established. So these are log gamma polymers, and that's joined to work by this by this group that also studied other related questions. And also you have the same for O'Connell-Yor polymers. That's a more recent work by Alberts, Rasulaga, and Simper. And also there are some, you can ask the same questions for zero temperature models. So these are geodesics in random potentials. I'm not going there in this talk. There's a recent work by Dunlop, Graham, and Rijik, and so they studied. So there's a PDE approach to the Burger's equation, and unlike ours, that is based on polymers. So they study the stochastic Burger's equation using PDE methods, which is sort of a natural thing to do, and that's great. But so they do not employ polymers at all. But I think it's just worth mentioning here. So, in a search of a new approach to polymer measures, I suggested to my student Hanbin to study Gibbs measures as invariant for stochastic gradient flow. I mean, this is a very old idea in finite dimensions. This goes back to Kolmogorov, I think. Tell me if maybe somebody knows better, but I think this goes to Kolmogorov's paper from 1937 on reversibility of the laws of nature. And so there he essentially says that Gibbs measures can be identified. So if you have energy in finite dimensions, so some energy, then you can define the Gibbs distribution, and then Gibbs distributions are invariant under the stochastic gradient flow. So the drift here is given by the gradient of the minus gradient of the energy, and there is this noisy elliptic additive noise with constant diffusion term that depends on the temperature. And in a sense, this is not a hard result. It sort of follows from Fokker-Planck equation, although you really have to work a little more to establish this. And the archetypal example in finite dimensions, or even in 1D, so that's this quadratic energy. So if you have quadratic energy, then the Ornstein-Uhlenbeck process is a stochastic gradient flow for this energy, and the unique invariant distribution, this Gaussian density. So this is what everybody knows, but this is sort of step one in understanding all this. So in finite dimensions, this is an old thing. Now in infinite dimensions, it turns out it's harder. First of all, the energy is not really well defined, and you have to work with infinite dimensional diffusions, these stochastic gradient flows, and so surprisingly, I still hope that it would be sort of easily manageable, but it turned out to be harder than I thought it would be. Still we can define this energy. It is defined only formally, right? Because it's infinite really on an infinite path. But it's if you perturb only a finite portion of the path, then the energy is perturbed by a finite number. And since the energy is local, you have dependence only on neighboring coordinates. You can make sense of this of this equation here. So you can still formally write it like this, and then decipher what it means in coordinates, and you'll get this equation that is in this blue rectangle. So you have a stochastic flow where the drift acting on each component is, well, it depends on neighboring coordinates. There is external forcing term, Fk, that is given by, remember a random potential. So there are two layers of randomness here. You have this external randomness that is that comes from the random potential. And then now I'm introducing a bunch of independent Brownian motions, one per coordinate. And I'm asking what can be said about the evolution of this. You can say that this is a stochastic heat equation because this term is really the Laplacian, or second derivative in finite differences. And then there is external perturbation. So this is a non-linear heat equation, and there is also a stochastic term, these Brownian motions. So each coordinate locally feels only neighbors. It interacts with the environment and picks up the, and also the external noise is acting on it. So this is the main result. On top, you see the same equation. There's nothing new. I just copied it there. So maybe I forgot to say. So you fix the endpoint. So this is the endpoint that doesn't move anywhere. So you fix it. So you pin the polymer, the infinite polymer at 0. And so that corresponds to this zero initial condition. And with Hanbin, we proved the following. There's a collection. This is a collection of results. Not every result from the paper made it to this statement. So you can make sense of this equation. So that's the first result. There is a solution map, and actually it makes sense as a random dynamical system. So there is a unique exceptional set on the potentials and on the Brownian noise, such that this forms what is known as cycle, or random dynamical system. So self-consistent flow of random maps. It is well defined on this space. So this is like we have to work with weighted norms, and this is only one of the norms that appears in the paper. So this is just for simplicity of presentation. And so it turns out that what you get is an order preserving continuous random dynamical system. Now, actually, a lot of work goes into this statement. You really have it's essentially PDE techniques, or stochastic PDE techniques. You work with Galerkin approximations, and there are embeddings, and so it's a really meaningful, contentful work. But I'm not going there because I'm going to talk about the dynamical properties. So what we prove is that for a fixed V, so now we fix V, and so the rest of these statements are fixed V. And then for almost every realization of the external potential of the environment, the set of polymers with the same slope V, so that is preserved by the dynamics. And so if you're interested in ergodic questions, well, it automatically means that you have infinitely many ergodic components. So if you start within one of them, you don't go any, you're stuck there. And also these sets as S of V, they're closed under this topology. So that's nice. So the mass doesn't leak out of these sets. So we prove that there is a unique invariant measure on each of them. There is a mixing statement. So it means that if you start with an arbitrary initial condition, the transition probabilities after time t converge to this unique invariant distribution. And this invariant measure coincides with the unique invariant, the unique infinite volume polymer measure on that set that we constructed with Ling in the previous paper. Moreover, there is a 1-force-1 solution principle on each of those ergodic components. So 1-force-1, if I have time, I'll talk about this. It's a form of synchronization. So basically all solutions in long term, they approach each other. And the proofs are based on a phenomenon that we call ordering by noise. And I will certainly talk about this. Now, there is a necessary remark that I must make here, that is, so the fact that infinite volume Gibbs measures can be identified as invariant for stochastic gradient flow. So in principle, this idea is not new. So there is a bunch of papers that have been authors that people have been studying this. In infinite dimensions, this is harder than in finite dimensions. And the part where Gibbs implies invariance, that's relatively easy, and that's valid under very broad assumptions. The fact that invariant measures have to be Gibbs, that's harder, and there are counterexamples where this doesn't hold true. And I'm referring to these papers. This is probably not exhaustive. And so initially, sort of naively, I thought that this wouldn't be hard, in our case. But it is not so easy because, well, partially because, we have this random environment, and these trajectories are the polymer paths. They are not really tame. They are allowed to grow linearly, and they pick up potential. So the potential is stationary, and so it can grow. And so if the polymer paths, if they can grow linearly with slope v, they can pick up pretty large values of those potentials. And so it's not, the existing theories didn't apply. And there are other instances where other theories could help, but they were not very helpful, in fact. Okay, so this is the main result. Let me try to talk about, why can this possibly be true? So if there's no external potential at all, then synchronization or one-force, one-solution principle is very easy to establish. So you just take, my goal is to say that all solutions do the same thing. So I take two solutions, so there's no external potential now, just the noise. So then it's discrete heat equation with fixed endpoint. Okay, so there's no spectral gap here, but still, if you subtract two solutions from each other, they now solve the homogeneous heat equation. So you have some contraction. So these solutions will converge to the difference will converge to zero slowly. If you take, if the initial conditions are, if they have the same slope, then the difference will converge to zero. And so the mixing will follow from this. And so you can derive that there's unique invariant distribution here. And of course, this is just Gaussian random walk that you can view as Gaussian free field. Now, this is not quite true if you take initial conditions with distinct slopes, because then the difference will converge to something, but not to zero. It will converge to a trajectory with constant slope. And this argument is true in any dimension, but then we know that polymers, in the presence of external potential, they do not behave quite in the same way in different dimensions. So there is a distinction between strong and weak disorder. So there are these things. So the rest of this talk is really one-dimensional. So now let us suppose that there is an external potential. It turns out that this random dynamical system preserves order. So if you start at time zero with two paths, and so one is completely on the right of the other, then they will stay like that for all times. So that's order preservation. And there is literature on order preserving stochastic systems, and it turns out that conditions that people use they're not quite, they do not work here. At least we couldn't make sense of, we couldn't apply that. Now there is an extra property here that is useful, and that's ordering by noise. So now suppose you have two initial conditions, and one has asymptotic slope V1 and another V2, and they're not equal to each other. On this picture, V1 is less than V2. And so it means that, you know, asymptotically, one goes this way, another goes this way. But there is a certain part where they are not monotone, where the, you know, the blue one is on the right of the red one at some places. So that is a finite part. But we prove that with probability 1, there is a finite time after which they get disentangled. And the mechanism that we use for this may be an overkill. And this is because I think that this may be true without additional assumptions, but this is what we end up using and imposing as an extra condition. So we require that these that there are arbitrarily large places in this random landscape that are close to 0. This is true for a broad class of Gaussian potentials or something based on Poissonian point field, shot noise fields. So if you have that, then we show that you can control your initial conditions into an area where the external potential is low, and then for a while the system essentially solves the stochastic heat equation, and that helps this monotonization. So if you have no external potential, then the statement that I'm stating here is definitely true. So we are able to prove that inevitably sooner or later these trajectories will enter such a domain where this disentanglement is going to happen, and these trajectories will become monotone. Once they become monotone, they stay ordered for all later times. And so, okay, so this is going to be really informal, not very mathematical, but due to this ordering by noise, which actually it's a noisy phenomenon, right? I mean, if there is no external noise, this is sort of a common theme in a large class of problems. If there is no external noise, these paths will just go downhill in the potential flow, and they will never get disentangled. But in the presence of noise, they eventually do. And so in the stationary regime, all these paths get ordered. I mean, you take two values of velocity or 100 of them, and if you wait long enough, and if you are in a stationary regime, they are all monotonized. So they get ordered, they are sorted by the dynamics. So there's this automatic sorting procedure embedded in this system. And since in principle there are uncountably many values of the velocity or slope, the asymptotic slope, it means that, and all of them are this sort of the same. They are shear images of each other. Like the dynamics for shear V is an image of the dynamics for slope 0. You just apply the shear transformation that I attempted to draw here. And if you have uncountably many values of V and things are monotone, then there's no space for having more than one possible value. So I mean, you have to work harder, a little harder to make this mathematical, but essentially possible values of those for each V, the possible values, possible paths worked out by the dynamics cannot occupy an interval. So you end up with 1 point. This distribution worked out by the dynamics. And so essentially this is the point of one force, one solution principle. The rigorous version of this argument is based on the notion of sample measures. So there's this general theory that claims that if you have an invariant measure for random dynamical system, for a Markov process that is generated by a random dynamical system, then you can consider this pullback procedure and represent this measure as a mixture of so-called sample measures. So you start back in an infinite past and see what comes out at present. And in the case where there is contraction in the system, like here, you have monotonicity and certain contraction. You can deduce that. Then you have this one force, one solution principle where the history of the forcing determines the present value, the present configuration of the polymer uniquely, and you end up with this. For each value of the asymptotic slope v, you end up with a unique global solution in this way. So this solution is plotted. It's a caricature, so it's plotted in red here. And if you start from any other initial condition with the same slope, it gets attracted to this main global solution. So you have, so on each of those components, you have a unique global stationary solution that attracts everything else. And the corollary of that is that the invariant distribution is unique. Because all these trajectories, they do the same thing. So asymptotically, they converge to this global solution. So that's a hand-waving argument why the invariant distribution has to be unique, and so it has to be Gibbs, because Gibbs are invariant. That's easy to prove in this case. And the same argument essentially proves mixing. So this is my last slide, and in this slide, I'm just trying to say that we think that all this holds in very broad generality. So you can consider broad class of polymer measures, other potentials. So maybe there's no Gaussian reference measures. Change the potential, change the dimension. Consider lattice models instead, where you have to replace the gradient flow with other, with discrete reversible Markov dynamics. So we think that in all these cases, one eventually will prove that for every asymptotic direction, there is exactly one infinite volume polymer measure concentrated on paths with that slope, and it coincides with the unique invariant measure given by the stochastic gradient or reversible dynamics, and there should be continuous dependence on V. So in this paper that I'm talking about, we sort of went, in a sense, in the wrong direction. So the hope is that you can use stochastic flows to deduce information about the Gibbs distribution. Now, in this paper, what we did is, we took the case of one-dimensional Burger's equation and the associated polymers, and we used the static polymers to deduce various all kinds of information about dynamic polymers. My hope is actually that the dynamical polymers will be useful in deducing various properties of Gibbs measures. And so, because you can, in principle, you can imagine that you have infinite dimensional stochastic dynamics. That is seemingly not too hard to study. So this is a heat equation with nonlinearity that is sort of tame. So these F, in this main equation, that well, maybe let's look here. So these F's, they grow quite slowly, and the noise is additive. So maybe it is not so hard. Well, maybe it's not so hard, but we don't know how to exploit the structure and obtain unique ergodicity, maybe using some existing methods or modifications thereof. But at this point, we don't know how to do that. Initially the hope is, you have so there's this, people have been studying unique ergodicity questions in infinite dimensions, and there are celebrated results. Jonathan is here, so he's responsible a lot for some of that progress. For one, there is a bunch of names and results, and so here you have certain regularity of transition probabilities, because the noise is elliptic; it acts on each coordinate. But then we're not like, is it elliptic enough really? Does it regularize the transition probabilities? It's not clear, because the dynamics really happens. These paths, they grow at infinity. It's not quite like you're in a Hilbert space where you have just finite Hilbert norm, and so coordinates just decay at infinity, and maybe you can split this into like high and low modes in some sense. No, here actually distant modes, distant coordinates are essential, and at this point we don't know how to overcome those difficulty. In general, irreducibility plus regularity, everybody knows that some combination of that should be enough. So this is a tormenting open question, and with that, let me finish here.
Okay, thank you very much, Yuri. And now we will listen to the discussion by Eric Bates. Oh, Yuri, can you please stop sharing the screen? Thank you.
Let me see that okay?
Yeah, it's a bit small, but I'm guessing you're going to zoom in.
I'll zoom in. I'll zoom in, of course.
Okay.
Right, so, yeah, thanks very much, Yuri, for the nice talk. Thanks very much to the organizers for the opportunity to respond to Yuri's talk. I have a few objectives. The first of which is just to give a very elementary and bird's eye overview or review of sorts of the program that Yuri has been pursuing with his co-authors over the last several years. And this kind of consists of three broad facets as far as I see it. So there's a Burger's equation that was the original motivation that Yuri laid out for us. Then there's the static polymer case. So this was the construction with Li and Li. And then there's the topic that Yuri focused mostly on today, which is the dynamic polymer perspective. And I'll try to kind of zoom in on each one of these pictures. And then with my second objective, I'd like to focus mostly on this polymer case because, well, this is my domain and what I am most interested in, and maybe the questions I can speak to most intimately. And there's a lot of interesting questions, and maybe I can give some inspiration there of guiding questions that others can take away. And then last, maybe I'll give Yuri some leading questions that might further the discussion at the end. Okay, so I'll start with, let me zoom in, and you can kind of see I've drawn the boxes around the things that are most relevant for the theory, and then outside the boxes there may be some external sources that you might reference. Okay, so with the Burger's equation, with the stochastic kick forcing, so this is a specific type that Yuri mentioned of a forcing mechanism, a driving force that I could choose for this equation. And this kick forcing ultimately will correspond, when I go down to the polymer perspective, of some notion of what I call weak solvability. So these polymers won't fall exactly into the class of exactly solvable models, but the specific choice of kick forcing is useful. And I'll try to give some intuition of why that's the case. Okay. And you can start with this Burger's equation motivation, and you can ask, as Yuri has kind of alluded to in a number of different parts, you could ask for certain properties of the solution theory for this equation. So ergodicity, right? And the ergodic components are characterized by the average value of the solution. And then when you flip over to the polymer perspective, this is corresponding to the slope of a polymer, which trajectory it takes asymptotically as you send time to infinity. You have a 1-4-1 solution principle, right? This is right here. So if you send an initial condition back to minus infinity, then actually the initial condition won't matter, just the realization of the noise and the ergodic component that you belong to. That's what will determine the solution at, say, a fixed time that you didn't send back to minus infinity, say time 0. Another thing that maybe Yuri didn't mention as closely, but I'll kind of brag for him, there's a continuity property as you send the viscosity parameter to 0. So mostly I think Yuri is focused on, at least in his talk, on positive viscosity. But then as you send this viscosity parameter 0, you can talk about the associated solution there. And the theory a priori is a little different, but you'd hope for a continuity statement. And indeed, he established this in this JSP paper with Liang. And then there's the standard hyperbolistic questions. So these would be questions more familiar to the SPD crowd. Although it kind of isn't in the right box here, this is stated in the positive viscosity case in terms of polymer measures. So it gives a nice interpretation of hyperbolicity in this positive viscosity case that you could work harder to try to further. And then the last thing I'll mention is the fact that really we're working in a non-compact setting, and this is important because, well, in the compact case, there's a rich history. Here I've just mentioned one paper, but there's many others you can find in the literature. And then you could also hope for a quasi-compact situation where maybe it's not a compact space a priori, but you impose certain conditions on the driving noise that make it such that you can confine the noise to mostly compact space. And so it's kind of still you're perturbing the methods that you used here in the compact case. But in the non-compact setting, and this was kind of starting with this JAMS paper back in 2014, and then Yuri explored the kick forcing setting in 2016. Now you actually do need a new perspective. So the non-compact case is relevant here and really demands a new set of tools. And I stress this because this is one of the reasons why the polymer perspective can be very useful. And Yuri, maybe if anybody wants him to comment further on that, would be willing to do so. All right, so now let me transition to this polymer picture. So again, just as a review, the Feynman-Katz formula is the way that you relate this Burger's equation with this kick forcing, ultimately down to a polymer Gibbs measure. And the partition function of that Gibbs measure is essentially related to the solution of the Burger's equation. Okay, so now once we've transitioned to the polymer picture, you can translate a lot of the questions from the SPD sense over to the polymer sense. And that's essentially what the CPAM paper with Liang did. Okay, so the key thing, as Yuri was pointing out, was this construction of the infinite volume polymer measure. And maybe I'll explain some of the ingredients that go into that, because these will naturally lead us into certain questions that are relevant for the polymer community, random growth models, percolation, et cetera. And maybe that can give some further intuition about where the literature might go in the future and what are the interesting questions there. All right, so first of all, the fact that you had a kick forcing solution and you can solve it using Feynman-Katz, this gives you this explicit free energy. And maybe this is the most solvable thing if you want to characterize some notion of solvability of this model. And namely that you have deterministic free energy that depends on the direction that you send the polymers. It's given by an additive constant alpha naught, which just depends on the distribution of the kick forcing. And then you have this deterministic parabola that gives you the directional dependence. And the fact that that's such a nice, clean parabola with no mystery behind it, it's an exact formula, that proves to be very useful. And indeed, in the random growth community, figuring out that there's a deterministic free energy, that's pretty standard. But actually determining a formula for the free energy, that's what is somewhat special here. And the fact that you have a parabola, which is kind of the simplest possible object with some nice curvature properties. That plays into the later ingredients. Most importantly, maybe this straightness property, which I'll get to. Okay, so this weak solvability that I've claimed here, which kind of results from the kick forcing, maybe that plays mostly into this computation. And again, this parabola term is just coming from the shear invariance of the Burger's equation. Okay. All right. So the second ingredient I'll mention, concentration. So this just says that this not only do you have a law of large numbers, but you have some concentration on a nice scale. Now here it looks like I'd have central limit theorem scaling, but in fact this is just an estimate that serves the purpose well enough. If you believe in KPZ universality, then you actually expect this exponent to not be 1/2, but instead to be 1/3. Okay, so that is an ongoing problem in the random growth literature in the KPZ world of verifying models with this 1/3 exponent and then seeing how far you can push that exponent. In general, we can't prove this. We can only kind of get something of this order, but for certain models, exactly solvable models, that is, we can actually prove to the 1/3. And so that's one interesting direction that the work lends itself to. The next ingredient I'll mention is this straightness property. So this just says that if I take a polymer measure, and let's say I'm looking at polymers that go in the direction B, so this is the asymptotic direction B, then asymptotically they should be essentially straight. Right? So if I look at the straight line between the endpoint and NB, so between 0 and direction B multiplied by N, then I shouldn't actually see polymers once I sample my Gibbs measure that lie too far away from this straight line. And this gives you some estimate of how far away. So you want something sublinear to say that it's asymptotically straight. The question is, how sublinear can you get? Again, end of the 3/4. This serves the purposes well enough for Yuri's paper, but KPZ would suggest that the exponent is actually smaller. You can get end of the 2/3. Okay, so that's another interesting direction that you might pursue. And the fact that I can't get these exponents, at least at the moment, for this particular model is why maybe we only call it a weak solvable model. Okay. And then the last property here, this last ingredient, is monotonicity. This is really a property that uses planarity. So this speaks to the issue of generalizing to higher dimensions and why you need a 1+1 dimensional model in order to prove some of these results. So this monotonicity, again, just says that if I have polymer measure here, it's in direction V, and I wanted to sample, say, a polymer measure that had a different endpoint that went down to, say, a lower V, then I could couple the two polymer measures such that the polymer I sample here is always above the polymer that I sample here. Right? So that's just the monotonicity principle. And that definitely relies on planarity. And this is an ongoing issue that we can prove things in 1+1 dimension, but when we go to higher dimensions, some of these monotonicity problems or properties go away, and then we run into trouble. Okay. And the last thing I'll say about this is that there is an alternative approach. So this circle of ideas, which ultimately leads to some convergence of ratios of partition functions to some random limit. This circle of ideas that leads to this originated in maybe the work of Chuck Newman back in the 1990s and his co-authors, but there is a different approach. You could just say, well, I know in the end I'm interested in these ratios of partition functions. In the 0 temperature world, these would be called Boozman functions in the limit. And so I could just look at that as the fundamental object and not worry about the geometry that led me there. The disadvantage is that I don't get insight into geometric questions, but I could just ask straight away about these ratios of partition functions. And that's the idea that's pursued in, say, these papers that give you an alternative direction to try to understand infinite volume polymer measures without understanding as much of the geometry at finite volume. So that's an ongoing question. Again, we're limited by 1+1 dimension. Saying there's infinite volume polymer measures in higher dimensions, that's an open problem, but a very important one. Okay. And then maybe the last comment I'll make is that we can ask about localization of these polymers. So very quickly, what this says is that, well, I told you this polymer, if I sample it, it should lie close to the straight line, and at least it should lie like end of the 2/3 away from that straight line. But that is a deterministic statement. If I allow myself to choose a random path to depending on the realization of the environment, then I should actually be able to choose a random path so that the polymer measure, when I sample it, lies within order 1 of some random path. So if I give myself the freedom to choose a random path, this n to the 2/3 turns into order 1. At least that's the conjecture. And we know certain results to this effect. It's well known in the endpoint localization. It's kind of starting to be established in the pathwise sense. But in all of these cases, it's not dealing with infinite volume, it's dealing with finite volume polymer measures. So there's an open problem there that's very natural, which is to pursue all these localization questions in the infinite volume setting. Okay. So a lot of interesting problems from the random growth perspective. And then allow me to not repeat most of what Yuri said with this dynamics case. There's all these nice properties, and I'll just say that the questions of pursuing dynamic polymers is interesting in its own right, at least for me. But then the issue of whether or not these things can say something about the finite volume polymers or the infinite volume polymers, existence of uniqueness of those infinite volume polymer measures, and whether or not they can say something interesting about the Burger's equation, all those things are yet to be explored. So this is a very interesting research program, and I hope I've given you at least some sense of why it's so interesting. So thanks very much.
Thank you, Eric. So Yuri, you want to comment on some points, or do we just go directly to questions of the audience?
Well, perhaps can you hear me, right?
Yes.
I mean, maybe I'll just reiterate one thing, that not so much is known about these thermodynamic limits, because there are just a few groups that have been working on them, and most of these results are sort of at the level of existence. If you can get existence and uniqueness, that's already a big deal. Besides that, the straightness results that were mentioned by Eric, we can also and we do prove them. In this new paper with Hong Bin, we prove them for thermodynamic limits. So these measures on infinite paths, they're also considered. Not only these paths are asymptotically, the slope makes sense for them, so they are linear plus sublinear fluctuations. We can quantify them to a certain extent, so they deviate at most by t to the 3/4. That's the estimate we can get. But again, so they should. Two more things should hold. They should be actually deviating by t to the 2/3. That's the KPZ scaling. And another thing is that it is tempting to conjecture that there is a random there's a random path that they localize around. And so we see that, and that's what Kostya Khanin and myself, that's what we wrote in a survey of ours that Eric cites here. We expect the polymer measure, the infinite volume polymer measure, also to localize around a certain random but one path, and the deviation should be like a stationary process. Now the localization results by Bates and Chatterjee, and a version of those by my student Nunghyang Seo and myself for continuous random walks. I mean, they are not. It's a nice. These are nice results, but they do not tell anything automatically about the infinite volume, about localization of the polymers of infinite lengths. But that seems a very interesting problem in itself. And so maybe that's what I wanted to say here.
Okay, thank you. So are there any questions in the audience for either Eric or Yuri? So
Kostya, you have a question?
Well, no, I don't have a question.
I mean, thanks for showing up.
Yeah, I'm following the discussion and enjoying your talk. I just want to say that, so maybe a right object. So what you discussed was this Gibbs measures with a fixed endpoint. So it's not like usually statistical mechanisms you want to consider on a whole kind of Z1. And that's not possible, of course, because points will come farther away. But what you can do, you can take this polymer measure kind of in between minus n and n, and then you shift the point at 0 to the origin. You kind of shift it so that it says near the origin. And then the polymer will not exist almost surely, but what will probably exist is a distribution, possible distribution of these polymers. So they will not exist because they're moving, but their distribution would have limit. Distribution of the polymer measures will have a limit when n goes to infinity. And that is an object which probably can be defined. It's one remark. And second remark, which may be also related to what Eric was saying, that yes, we have localization property, but recently we looked with Li and Li, we were doing numerical studies of this say endpoint of a polymer of length n, which is localized in a strong disorder regime, and then we just look at the point. What is the variance of this endpoint? We are not averaging with respect of environment. We just look at the typical environment, the variance of this endpoint, and it turns out that it's growing. It's growing with the length of polymer, which was a surprise to us because we thought that typically it would be order one because this is we don't know really what's going on, but it looks like that the limiting distribution of this order one limiting distribution has heavy tails. So heavy tails, that variance doesn't exist for this limiting distribution, and that is possible explanation of this fact. So there are interesting.
So did you try to compute some other statistics, like not variance?
We did try to look at this. We will look around. We're trying to see different statistical properties, but it looks to us more likely that the explanation is that the limiting distribution, this order one limiting distribution, has heavy tails, which is again surprise because for toy models it's not the case. And so there are interesting questions about the behavior of the polymers in dimension 1+1, which they're not question of a type of KPZ scaling. They're just question about localization properties and how strongly it's localized. And we don't know yet the answer, but there are some surprises numerically, which we saw and which we recorded. So that's what I wanted to say.
Thank you.
Thank you. So actually, I had one question for Yuri, something I didn't quite understand. In your talks, you're talking about what you called ordering by noise. But it was not clear to me. I didn't understand why noise is helping for this ordering. How is
Oh, this is a very general theme in I don't know, like in machine learning, in statistical mechanics, and anything. You know, if there is no noise, you know, and you are in a potential, just go downhill. You can't, you know, you get to the closest local minimum, and just stay there. You know, infinite time. You know, you approach the minimum exponentially fast. So that's very boring dynamics. Nothing much happens. In the presence of noise, it turns out it's guaranteed that the system explores much broader and maybe the entire space. And this is a very general thing. You know, the evolution, biological evolution is based on this, or, you know, theory of metastability. You know, this essentially describes these rare transitions between various potential wells. So this is a theme that is that sort of penetrates the entire modern applied stochastics.
okay? Thank you. Thanks, Sophie. So thank you again, you and Eric, for your talks.